Hello and welcome. In this worked example, we've got two balls, X and Y, moving towards each other with speeds 5 and 15 meters per second, respectively. They make a perfectly elastic head-on collision, and ball Y moves to the right with a speed of 7 meters per second. We're interested in the speed and direction of ball X after the collision. Let's jump over to the chalkboard. Because this is a perfectly elastic collision, we know that the kinetic energy is going to be conserved. Now, we don't know the mass of this object, we don't know the mass of this object, we're only given their velocity. Thankfully, by combining the law of conservation of linear momentum and the law of conservation of energy, namely the fact that kinetic energy is conserved in this type of collision, we can arrive at an idea, which we won't do right now, but if you click on the link above, you can see it, that the relative speed of approach is going to be equal to the relative speed of separation. So we only consider sort of how fast these objects see each other. And you, as a student of physics, just have to know, well, how do I calculate relative speed? When objects move toward each other, we add their speed to calculate the relative speed. Which kind of makes sense, like if two objects are passing each other on the highway, they each see each other at a much faster speed, because like this thing is approaching this one at 15 meters per second, while this thing is speeding towards it at 5, so they see each other at a relative speed of 20 meters per second. If the collision is perfectly elastic, that's how fast the objects will see each other after the collision. So this thing is moving off to the right at 7 meters per second. There's only certain possibilities for what this sphere could be doing in order to give us sort of the relative speed here, 20. If the object is moving to the right, then they'd be going in the same direction, and we'd have to subtract. And so this object would have to be going 27 meters per second. And so if it's going to the right, it'd have to be going at 27 meters per second. So 27 minus 7 would be 20. But how could this thing like pick up speed in the same direction if this thing is going faster? And so it kind of doesn't make sense, that we would get a vector going this way. So what's more typical is that these things are going to crash into each other, and this thing gets turned around and moves off this way, and this thing might be going in the other direction. So they're still going to be going in opposite directions, like towards each other or away from each other. And when they're moving in opposite directions, again, we add. So it's well, what number do I add to 7 to get 20, right? The relative speed of approach. So this thing could be moving to the left at 13 meters per second. Okay, and I think that's one of our answer choices. Let's see. So we see 13 meters per second to the left, choice B. If we're moving to the right, again, we'd be in the situation where if they're going in the same direction, we'd have to subtract, and 13 minus 7 is 6, which does not equal the relative speed of approach. So choice B is correct for this question.